Now, just because a reaction occurs doesn't mean that it's usable. We have to be able to influence the rate of the reaction. Sometimes reactions happen too fast. Sometimes they happen too slow. So we have to be able to make these reactions occur at the rate that we want them to. First of all, we have to talk about how the reactions actually occur. Reactions occur because molecules collide and supply energy. If we were to look at a graph of energy versus number of particles that have a certain amount of energy, we would have a graph that looks like this, a nice bell-shaped graph. Now, in order to react, let's say they need this amount of energy. So only these particles in this region of the curve have enough energy to react. If we want a reaction to go faster, we need to increase the number of particles in that area. If we want to make it go slower, we need to decrease the number of particles in that energy. How can we influence that? One way is concentration. Concentration just means we have overall more particles. So if we looked at our graph again, and it started like this, by increasing the concentration, we would change our curve so that it looks like this. I know. So we've got more particles under the curve here that have enough energy. So just by having more stuff there, we should be able to make our reaction go faster.
Next reaction, we're going to look at what happens with concentration and rate of reaction. What I'm going to do is I'm going to take some zinc metal. Zinc metal reacts with hydrochloric acid quite readily to form hydrogen gas. I'm going to stick a piece in each one of my flasks, about an equal sized piece. And now, come around the other side of the table. I'm actually going to flip this over. I'm going to put some hydrochloric acid into this one. Swirl it around and we can look at the reaction that happens. See the reaction going on in there? Not much. A couple of little bubbles being formed on there, but not a whole lot. That is hydrochloric acid, that is zinc, they are reacting. Very, very slow. Why? This hydrochloric I put in there is very, very dilute. Not a lot in there. Into this one, this is concentrated hydrochloric acid. I'm going to put a little bit of this in there. And boy, you can see, even from way back there, look how fast that's reacting. That's because I've got more hydrochloric molecules, particles, that can react in there because of the higher concentration.
Factor. Surface area. If we increase the surface area, we increase the rate. That's because the only particles that can react or collide are the ones on the surface. So by increasing the surface area, we increase the number of particles that could be there.
In this reaction, we're going to look at surface area and see how surface area is influences rate of reaction. I'm going to take some methanol and pour it into a little dish here. Now methanol is highly flammable, we know that. So I'm going to take my matches, I'm going to light a match, and light the ethanol. And it burns fairly rapidly. Still burning, still going at it. Nice blue flames, hard to even see. But if I want to make it burn faster, that's still burning, I'm going to stick it over here. What I'm going to do this time, I'm going to take this container. And into my container, I'm going to put some methanol. About the same amount as I put in the dish. And then I'm going to swirl the methanol around in there. As I swirl the methanol around, what it's doing is it's spreading out throughout the entire container. Now if I try to light it, bring my match close, it all burns within just a couple of seconds. You can hear the big whoosh as the alcohol burn very, very rapidly. So the more, we're going to look at another reaction that involves surface area. I have here my Bunsen burner. Turn my Bunsen burner on to get some flame going. This is what's called lycopodium powder. It's actually a spore. But it's a very, very fine spore. It makes a very, very fine dust. I pour it on the table. I turn my burner on it. It burns a little bit. But if I can take this powder and instead of having it in one pile, I spread it out like that by throwing it into the flame. See if I can scoop that up. It burns much more rapidly. Here's I've got a water bottle with some in it. And if I squirt some lycopodium powder through there, you can see it burns very rapidly. Now we'll try another demonstration with lycopodium powder. Let's say I take my lycopodium powder and I put it into a bucket. Alright, it's all just laying in the bottom of my bucket. Or a little bit more in there. Now I put a cover on it. Alright. Now, if I take my bucket and I shake it up, what that does is put all that lycopodium powder floating around in the air in there. And I stick my lighter inside there. You can see we get it to burn inside.
Temperature. If we increase the temperature, what happens is we shift this curve over to the right. Because temperature means energy. So even though we've got the same number of particles under the entire curve, now we've got all of these particles that can react. Which means that if we increase the temperature, we increase the rate of...
What effect temperature has on the rate of a reaction. I've got in here some thiosulfate. Thiosulfate solution, combination of sulfur and oxygen. Now when thiosulfate comes in contact with an acid, it starts to react and it produces elemental sulfur inside my solution. So I'm going to take my solution, which is at room temperature, I'm going to add in some little bit of acid. And then I'm going to shake it up. And if you look at my test tube, you don't see much happening right now. But the two are together and they are reacting. And there's producing some sulfur in there. Just not a lot at this point in time. It's really kind of a slow reaction. As soon as we produce enough, then we'll see it. It'll start to get all cloudy in there because we get enough sulfur that we can actually see it. So what I'm going to do is I'm going to take this one and I'm going to sit it right here in our test tube rack. keep an eye on it as it gets cloudier and cloudier and cloudier until it gets cloudy enough that we can actually see that it is indeed reacted. In fact, if I bring it over now, I take a black ruler, you can see that it is getting pretty cloudy right now. So you can see the sulfur forming in there. But that took a good bit of time in order for it to happen. Over here, I've got another test tube of thiosulfate that I put into some water that's hot. Now if I take this hot thiosulfate and I put some hydrochloric acid into it, about the same amount, and I give that a shake, now notice that it's turning cloudy already. It's completely cloudy. Notice how much faster that reaction occurred when it was hot as compared to when it was cold. They're about at the same point, but this one was much, much faster than this one.
The reaction. The last thing that we can do is to use a catalyst. What a catalyst does, at least what we think it does, is in our energy diagram, we have our reactants and our products. And in between, we have an activation energy. What we think happens with adding a catalyst is somehow that activation energy becomes less. Catalysts, by definition, increase the rate of a reaction, but they are not used up. In other words, they're not actually part of the reaction. Somehow they lower the activation energy. The opposite of a catalyst is an inhibitor, which makes a reaction go slower. In the case of foods, we would call that a preservative.
All right, the next reaction here involves a decomposition reaction. This one actually involves hydrogen peroxide breaking down into water and oxygen. This is a solution of hydrogen peroxide poured into my flask here. Now this is a very concentrated solution, about 5 times more concentrated than what you buy in the drugstore. But if you look at it, there's really not much happening. It's not breaking down into water and oxygen very fast. It is breaking down, it just takes a very long time to do it. If I want it to break down faster, I'm going to add into here a catalyst. Now the catalyst for this reaction is, there's a number of different catalysts. I'm going to use potassium iodide. I'm going to add a little potassium iodide in there. Give it a little bit of a swirl to get it to dissolve. And you can see that I've got some bubbles forming at the bottom. And those bubbles are getting more and more and more. The reaction is going much, much faster than it was without the catalyst. And there's actually a lot of heat being produced. You can actually see some steam coming out of the top of the bottle now. And that reaction is going to go on. Now as it finishes up, a lot of heat, there's a lot of steam, that's mostly steam coming out of there as the water that's left behind boils. There's also a lot of oxygen, that's what's bubbling out of there. And then in a couple of minutes, all the hydrogen peroxide will be used up, and we'll just have water down here with a little bit of potassium iodide dissolved in it.